Welcome to today's session. We're exploring the queue data structure, a key concept in computer science. I'll start from the basics, cover the main operations, provide pseudocode to show how they work, and explain their time and space complexity. Let's dive in and make this clear and straightforward. What is a queue? A queue is a linear data structure that stores elements in a specific order, following the first-in, first-out FIFO principle. This means the first element added is the first one removed. Picture a line of people waiting at a ticket counter. The first person in line gets served first. Elements are added at one end, called the rear, and removed from the other end, called the front. Key characteristics. FIFO order, first in, first out. Two ends. Add elements at the rear in queue. Remove them from the front to queue. Dynamic size. Queues can grow or shrink as elements are added or removed. Real-world example. Think of a printer queue. When you send multiple documents to print, the printer processes them in the order they were sent. The first document in is the first one printed. Types of queues. There are several types of queues, each with unique features. Let's go through the main ones. Simple queue. A basic queue where elements are added at the rear and removed from the front. It's like a straight line of people waiting. Circular queue. The queue forms a circle, where the last element connects back to the first. This is useful in systems with limited memory to reuse space efficiently. Priority queue. Elements are assigned priorities, and the highest priority element is removed first, regardless of when it was added. For example, in a hospital triage system, urgent cases are treated first. Dequeued double-ended queue allows adding and removing elements from both the front and rear, offering more flexibility than a simple queue. Queue operations. Now, let's cover the core operations of a queue. These are the actions you can perform, and I'll explain each with pseudocode to clarify each step. Operation 1. In queue, add an element. This operation adds an element to the rear of the queue. Explanation. Enqueuing places an element at the end of the line. For example, if you're in a queue at a coffee shop, a new customer joins at the back. Let's see the pseudocode. Check if the queue has reached its maximum capacity. Return error if no space is available. Store the element at the rear position. Move rear position to the next empty slot. Indicate successful addition. Example. In a simple queue with elements A, B, C, enqueuing D results in A, B, C, D, with D at the rear. Time complexity. O of 1. Adding an element at the rear is a constant time operation, as it involves updating the rear position and inserting the element. Space complexity. O of 1. Only one element is added, regardless of the queue's size. Operation 2. Dequeue remove an element. This operation removes and returns the element at the front of the queue. Explanation. The first element in the queue is removed, and all other elements shift forward. It's like serving the first person in line at a ticket counter. Let's see the pseudocode. Check if the queue has no elements. Return error if queue is empty. Store the front element for returning. Move front position to the next element. Return the removed element. Example. In a queue ABC, dequeuing removes A, resulting in BC. Time complexity. O of 1. Removing the front element is constant time, as it only involves updating the front position. Space complexity. O of 1. No additional space is needed beyond the queue itself. Operation 3. Peek view front element. This operation returns the front element without removing it. Explanation. It's like checking who's at the front of the line without serving them. Let's see the pseudocode. Check if the queue has no elements. Return error if no front element exists. Return the front element without modifying the queue. Example. In a queue ABC, peeking returns A without changing the queue. Time complexity. O of 1. Accessing the front element is constant time. Space complexity. O of 1. No extra space is required. Operation 4. Is empty. Check if queue is empty. This checks if the queue has no elements. Explanation. If there are no elements, the queue is empty, like an empty line at a store. Let's see the pseudocode. Check if front position equals rear position no elements. Indicate queue is empty. Indicate queue has elements. Example. A queue with no elements front equals rear returns true for is empty. Time complexity, O of 1. Checking the front and rear positions is constant time. Space complexity, O of 1. No additional space is used. Operation 5. Is full check if queue is full. This checks if the queue has reached its maximum capacity relevant for array-based implementations. Explanation. In a fixed-size queue, if the maximum capacity is reached, no more elements can be added. Let's see the pseudocode. Check if rear position has reached the queue's maximum size. Indicate queue is full. Indicate queue has space available. Example. In a queue with a maximum size of 5, if 5 elements are present, is full returns true. Time complexity, O of 1. Checking the rear position against the maximum size is constant time. Space complexity, O of 1. No extra space is needed. Implementation of queues. Queues can be implemented in two primary ways, using an array or a linked list. Let's explore both, with pseudocode for initialization that's language independent and includes comments. Array-based queue. How it works. Uses a fixed-size array to store elements. The front and rear indices track the first and last elements. Pros. Simple to implement. Fast access due to contiguous memory. Cons. Fixed size can lead to overflow. Dequeuing leaves unused space unless using a circular queue. Example. In an array ABC space with front equals 0 and rear equals 3, enqueuing D sets rear equals 4, and dequeuing A sets front equals 1. Pseudocode. Create an array with the specified maximum size. Set front index to the start of the queue. Set rear index to the start empty queue. Return the initialized queue. Time complexity initialization, O of 1. Setting up indices is constant time. Space complexity, O of n. The array requires space proportional to the maximum size n. Linked list-based queue. How it works. Uses nodes, each containing data and a reference to the next node. The front and rear indices track the first and last nodes. Pros. Dynamic size prevents overflow. Efficient memory use as nodes are allocated as needed. Cons. Slower access due to non-contiguous memory. Requires node management. Example. A linked list A to B to C. Enqueuing D adds a node at the rear, and dequeuing A removes the front node. Pseudocode. Set front index to null empty queue. Set rear index to null empty queue. Return the initialized queue. Time complexity initialization, O of 1. Setting indices to null is constant time. Space complexity, O of 1. Initially, no nodes are allocated. Thanks for learning with me today. In the next video, we'll dive into circular queues, priority queues, dequeues, and more applications of queues. Stay tuned.